In section 7.3, we are going to talk about how to integrate trigonometric expressions. Now, from Calculus 1, we probably know some basic ones, but we are going to do some products and some quotients of lots of different trigonometric expressions and show some different techniques for evaluating them. I'm going to break this video up into a couple parts. In this first video, I'm just going to concentrate on sine and cosine because there are actually two different ways that we need to treat sine and cosine integrals, and it all depends on what kind of powers that we see, what kind of exponents we see in our integrand. So right now we're just going to deal with sines and cosines. If you are asked to integrate some expression with sines and cosines and possibly powers of sines and cosines, what you need to keep in mind, and we will write this down to help us. The derivative for sine is cosine, and the derivative for cosine is negative sine. Now I'm writing derivatives down because all of these are going to involve u substitution in some way or another. So we need to keep in mind what these derivatives are so we know if our u substitution is going to work or not. One other really important formula that we're going to need in order to do these problems is the Pythagorean identity that relates sine and cosine, which is sine squared plus cosine squared equals 1. We are going to use this formula to hopefully replace sines with cosines or to replace cosines with sines, and we will see that as we look at some problems. But the first thing you should check when you're asked to integrate some expression that has sines and cosines in it, especially if it's just a product or a quotient of a bunch of sines and cosines, is you need to look at the powers. And you need to see if you have an odd power, or at least one of the powers odd. And if so, this is going to make it a lot easier. So what I mean by this, some expressions that have an odd power, if we were asked to integrate sine cubed x times cosine to the 4th x. So one of the powers here is odd. Sine has an odd power. We could be asked to integrate sine squared x times cosine to the 5th x. And again, one of our powers is odd. So that's good. They could also be odd, and that would be fine also. So sine cubed x cosine to the 7th x. Now here both of them are odd. So all we're asking is at least one of the exponents odd? And if it is, then the approach that we're going to take is to just hold on to one of those odd powers and but let's say rewrite the rest of them in terms of our other function using that Pythagorean identity. So if the answer is yes, then great. I think this is the easiest method to use. We're going to keep one of them, and we're going to switch all the rest of them into our other trig function. And the way that we switch is with our Pythagorean identity. Notice that our Pythagorean identity does not have odd powers, it has even powers. So the Pythagorean identity can only be used to switch over even powers of sine and cosine. But if we have an odd power, we just said we're going to keep one of them. So if I keep one of them, so you're going to take one away from an odd, you'll always be left with an even number, and we will be able to switch all of the rest of them over using our Pythagorean identity. Once we're done with all of the algebra manipulation, we should be left with something that we can integrate with u substitution. So if we were asked to integrate sine cubed times cosine to the fourth. Sine cubed times cosine to the fourth. Now I know the derivative for sine is cosine, the derivative for cosine is negative sine. So there is a good potential for u substitution to work here. The issue right now though is the powers. If I were to let u equal cosine, the derivative would only be one sine, and I have three sines. So what we need to do is we need to identify our odd power, if we have an odd power, and we're going to do it this way, and we're going to rewrite this expression so that, and I'm going to drop the integration for now and just work with my integrand. I'm going to break apart my sine cubed into just a single sine and a sine squared. That still is sine cubed, but it's going to be a lot more user-friendly for what we need to do here. So we're going to keep one of them, and we are going to switch the rest of them over into our other function using the Pythagorean identity. So in this case, since we're working with sines and cosines, sine had the odd power. We're going to hang on to one of those sines, and we're going to switch the rest of our sines into cosines. Now, the Pythagorean identity says that sine squared plus cosine squared equals 1. But I want to know what I can replace sine squared with. So I'm going to solve this equation for sine squared. In order to do that, I've got to subtract the cosine squared over to the other side. And this is going to give us an expression to use so that we can replace the sine squared with cosines. So I can replace sine squared with 1 minus cosine squared. So now we've got the expression sine x, we're holding on to that one, and then I've got, instead of sine squared, I've got 1 minus cosine squared, and then I also have my cosine to the fourth. We're not doing anything with that one because that didn't have an odd power. Right now we're just working with our odd powered trig function. At this point I have everything in terms of cosine, except for this one little sine that I've decided to hold on to in the front. And the reason I've decided to hold on to just one of them is because if you were to do a u substitution now, we're going to let du equal cosine because we have so many of them. And not du, sorry. We're going to let u equal cosine. And then du is going to take care of the sine for us. It doesn't matter that the derivative is negative sine. That negative is just considered a coefficient, and coefficients don't give us any trouble in integration. They just get carried on to the answer. If you want to, we can divide that negative sign over to the other side. I would not suggest changing it to cosecant though. We want to keep everything here in terms of sine and cosine. So now we're going to do some replacing. I'm going to replace all of my u's with cosine, and I'm going to replace my dx with negative 1 over sine x du. And we'll see what happens to this integral. I'm replacing all of my cosines with u. And I'm replacing dx with negative 1 over sine du. And you see those signs are going to cancel each other out. The negative doesn't go though. The negative is going to stay. I am going to go ahead and use that negative to switch around my subtraction here. So now we've got the integral of u squared minus 1 times u to the 4th du. And we're going to go ahead and distribute our u to the 4th as well. Then we could just integrate this using power rules. That's going to give me u to the 6th minus u to the 4th du. Now it's a very simple power rule integration. So we get 1/7 u to the 7th minus 1/5 u to the 5th plus c. And the last thing you have to do is plug back in what you said the u was going to be. So it's important that you write this stuff down because you're going to have to refer back to it later. We said u was cosine. So I need to go back here into my answer and replace my u's with cosines. So 1/7 cosine x to the 7th minus 1/5 cosine x to the 5th. That is our antiderivative. As long as we have an odd power to work with, these are pretty easy. If you have an odd power, you can always hold on to one of them. And the purpose of that one that we're holding on to is to cancel off when we do the u substitution. So let's look at another one. What if we were asked to integrate sine to the 5th, and I'm actually going to change this around, sine to the 4th times cosine to the 5th. So anytime you see a sine cosine integral, you should check to see if you have an odd power. And we do have an odd power here. If you have an odd power, that is the function we want to break apart. So my sine to the 4th, cosine to the 5th, I need to get it rewritten. Now my sine to the 4th is fine for now. We're not going to do anything with that because that had an even power. My cosine to the 5th, I'm going to hold on to one of them. And if I do that, I'll have 4 left. Remember though, your Pythagorean identity can only switch over squares. So I'm actually going to do one more rewrite of this expression, and I'm going to break that cosine to the 4th into cosine squared times cosine squared. And just like we were able to solve our Pythagorean identity for sine squared, just the same way we can solve for cosine squared and figure out an expression to replace cosine squared with. And it turns out that cosine squared is equal to 1 minus sine squared. And I'm replacing both of them. I want to replace everything that has an odd power. I'm going to hold on to one of them and replace all of the rest of them so I can switch them over into my other trig function. So now my cosine to the 4th is rewritten as expressions with sines. So now we are ready to integrate because now this will work with a u substitution. I've got everything written in terms of sine except for that one little lonesome cosine, which I'm just holding on to, so my u substitution will work. So we're going to let u equal sine this time because we've got tons of sines in there. And we want our du always to come out to be the one that we're holding on to. And that will be true here. If u is sine, then du is cosine x dx. Which means we can replace dx with 1 over cosine x du. You don't necessarily have to solve for dx. Depending on what you were taught in Calculus 1, you could potentially keep those together. It's up to you. But now every time I see a sign, I'm going to put a u instead. So this is u to the 4th times cosine x times 1 minus u squared times 1 minus u squared, and then instead of dx, I'm putting in 1 over cosine x du. And just like in the last one, don't rewrite your 1 over cosine as a secant. The whole point of that 1 over cosine is to cancel with this cosine I was hanging on to. So now it's just an algebraic expression that we have to integrate. And to integrate this by hand, we're going to have to do some foiling and some distributing. I guess first I'm going to go ahead and FOIL these guys. And that's going to give me 1 minus 2u squared plus u to the 4th. And then I can go ahead and distribute my u to the 4th. And then we'll have a nice simple polynomial to integrate. So we've got u to the 4th minus 2u to the 6th plus u to the 8th. And we can just integrate with power rule. So we get 1/5 u to the 5th minus 2/7 u to the 7th plus 1/9 u to the 9th plus c. And we want to change this back into a trigonometric answer. Remember, our u this time was sine. So every time I had a u, I'll replace it with the sine for my final answer. 1/5 sine x to the 5th minus 2/7 sine x to the 7th plus 1/9 sine x to the 9th plus c. And that is our antiderivative. We're going to look at one more really quickly, and then we're going to talk about what you are going to do if you don't have an odd power to work with. So in this last one, they're both going to be odd, which means you've got the choice of which one you want to split apart and which one you want to keep. So in this one, we're going to have sine cubed times cosine cubed. We've got sine cubed times cosine cubed. Now remember, the question we were to ask ourselves is at least one of our exponents odd? And the answer is yes. We have at least one odd exponent. We actually have 2 odd exponents. And when you have 2, that means you get to choose which one you want to break apart. So I'm just going to go ahead and break apart my cosine. That's going to put everything in terms of sine. I personally think that's going to be a little bit easier because then my u substitution will be for sine and my du will be cosine. It avoids that extra negative that we got in the first problem that we did when our u was cosine. So I'm going to consider this one to be the odd power that I want to break apart. And I'm just going to ignore the sine cubed for now. So I've got sine cubed x. For my odd power, I'm going to hold on to one of them, and I'm going to rewrite the rest of them using the Pythagorean identity. So this turns into sine cubed x times cosine x times 1 minus sine squared x. So now we're integrating sine cubed times cosine times 1 minus sine squared. Now I've got everything written in terms of sine except for this one little lonesome cosine, and he's very important. We're holding on to him so that our u substitution will work. I'm going to let u equal sine because I've got so many sines in there, and then whatever one I was holding on to, remember, I want that one to hopefully turn out to be my derivative. And the derivative of sine is in fact cosine. And we can rewrite this integral in terms of u. So everywhere I had a sine, I'm going to replace it with u. So I've got u cubed times cosine x times 1 minus u squared. And then instead of dx, I'm going to put 1 over cosine x du. And the whole point for that was for my cosines to cancel. Now again, we've got a simple algebraic integrand that we can do by hand, just using power rules. We just have to go ahead and distribute that u cubed. And if we do that, now be careful, when you do u cubed times u squared, we are multiplying the bases, which means we are adding the exponents. So it's going to be u cubed minus u to the 5th. Our antiderivative comes out u to the 4th times a quarter minus 1/6 u to the 6th plus c. And now all we have to do is replace the u's. And we had said u is going to equal sine this time. So because I chose to hold on to a cosine and do u substitution for sine, I have a final answer in terms of sine. It's possible that if you choose to do it the other way, you will get an answer in terms of cosines. And that is perfectly acceptable because we have this Pythagorean identity up here that links sines and cosines. Remember, sine squared is equal to 1 minus cosine squared, and vice versa. Cosine squared is equal to 1 minus sine squared. So it is possible to get an equivalent expression, to get an equivalent answer that has cosines in it. So there is a second correct answer for this problem, since both of our powers to start with were odd, and I just kind of arbitrarily chose cosine to split apart. Now, if we don't have an odd power to work with, we're going to have to do something very different. If there are no odd powers, then we're not going to be able to hold on to one of them and have all even powers left over, where our Pythagorean theorem can switch all of them to the other function. If there are no odd powers, that means all of them are already even, and there's no little oddball guy to hold on to. So what we're doing here with this situation is we're going to use a power reducing formula. And there are two of them that are going to come in handy. The first one says that sine squared is equal to 1 minus cosine of 2x all over 2. The cosine squared formula is very, very similar. Cosine squared x is equal to 1 plus cosine 2x over 2. So the only difference here is that for sine we've got subtraction, and for cosine we have addition. Everything else about these formulas is exactly the same. This is a power reducing formula because we're starting with something that has a squared in it, and we're going to replace it with something that does not have a square in it. Starting with a square, replacing without a square. But an important thing to note here is that when you do this, your angle doubles. Whatever your angle was originally, your new expression is going to have double that, which is pretty easy to deal with. All we have to do is divide by the derivative of our angle. Very similar to what we do when we have exponential functions with linear exponents. We just divide by the derivative of the exponent when we do our antiderivative. These functions are exactly the same. To deal with a trig function with a linear angle, we would do the normal trig antiderivative, but then we'd also have to divide by the derivative of the angle. So if there are no odd powers to work with, what we have to do is use these power reducing formulas and possibly replace multiple times until we're left with an expression that has no powers. So you may have to perform multiple substitutions. until you arrive at an expression that has no exponents. And what I mean by that is just all of our exponents are ones. If we don't see an exponent, that means we've got a little imaginary one here. So we'll start off very simple. If we were asked to integrate sine squared. Now technically, I haven't said this yet, but it is good to know. Sine squared x is the same thing as sine x inside parentheses with a square on the outside. When you look at it in that format, it's a lot easier to see that this is a composite function. And typically with composite functions, we do a u substitution. We would let u be equal to the inside, and then du hopefully would cancel off anything else in the problem. But the issue with these is that there isn't anything else in this problem besides the composite. And if u is going to be equal to a trig function, the derivative of one trig function is always another trig function. But I don't have any other trig functions in this integral that need to get canceled. So u substitution here is not going to work. What we need to do instead is use our power reducing formula. Anytime we do not have odd powers to work with, you should use your power reducing formulas. So for sine squared, I'm going to go ahead and replace it with 1 minus cosine of 2x all over 2. And this is actually a lot easier to work with if we separate the numerator. And we think of this as integrating two separate terms. So I'm going to do 1 divided by 2 minus, and then instead of saying cosine of 2x over 2, dividing by 2 is the same as multiplying by a half. I think that looks a lot nicer than having to integrate cosine 2x over 2. Now this one's very easy to integrate because the antiderivative of 1/2 is 1/2 x. The antiderivative for cosine is going to be sine of the same angle, but then you also have to divide by the derivative of the angle, which is 2. So that's going to put an extra 1/2 out front. So we get 1/2 x minus 1/4 sine of 2x plus c. So let me write that little rule out kind of like I did with my exponentials. Anytime we're integrating, and this could be true for sine or cosine, where it has a linear angle, if it's a plain old x, we just do it normal. But if it's x times something, you could write out a u substitution for the angle, but it's every single time it's just going to come out to be 1 over the derivative, and then your normal antiderivative. The antiderivative for cosine is sine. This is only if our angle is linear, which means x has a power of 1. This is ultimately what the result of a u substitution is going to give us every single time. So it's kind of a little shortcut formula. So that's all I did here. I recognize that the antiderivative of my angle was 2, so it's going to throw an extra half out front. I already had a half out front, and now antiderivative is going to put another one out there. And we're going to look at one more because they're not all this simple. If we have to integrate, let's say cosine to the 4th x dx. So the question we ask ourselves is, do I have an odd power to work with? And the answer is no. If the answer to that question is no, you'll have to do power reducing formulas. Now this power reducing formula is for sine squared and cosine squared. And if we don't have any odd powers to work with, that means we have all even powers. All even numbers can be broken down into a string of 2's. So my cosine to the 4th I can write as cosine squared, cosine squared. And then I'm going to replace both of them with their power reducing formula. So this is going to turn into, remember for cosine it's the same formula but with a plus. So that didn't seem too bad yet, but we're nowhere near done. My suggestion when you're working with these power reducing formulas, I'm going to go ahead, since this is a product, I can go ahead and multiply my denominators together as 4 and bring it out to the front as a 1/4. And I'm left with 1 plus cosine of 2x times 1 plus cosine 2x, which we're going to have to FOIL that out. I can't leave that as a product and do the antiderivative. So if we FOIL this, we're going to get 1 plus 2 cosine 2x. So far, both of those are very easy to integrate. But then cosine 2x times cosine 2x is cosine 2x squared. So remember what I said earlier. I said we're going to have to keep performing multiple substitutions possibly until we arrive at an expression that has no exponents. In other words, exponents of 1. We don't want any extra exponents. So my first term is fine. We can integrate that. My second term is fine. We can integrate that. But the third term has an exponent. It's got an exponent of 2. So we're going to have to do a power reducing formula just for that piece. I'm going to leave everything else alone, and I'm going to say cosine squared is 1 plus cosine of, now remember the angle doubles. Here it was 2x, so if I'm going to apply my power reducing formula again, it's going to jump to 4x. Now you cannot bring that divide by 2 all the way out front with your 4th, and that's because the divide by 2 does not apply to all of your terms. It only goes with that last term that we have in there. So instead I'm just going to go ahead and separate them. But we're pretty much ready to integrate here. I've got 1/4 of the integral of 1 plus 2 cosine 2x plus a half cosine 4x. And look, these guys are like terms. I've got a 1 plus a half. If you want to, you could rewrite this one more time just to reduce the number of antiderivatives you have to find. They combine and make 3 halves. Now we can do all of these antiderivatives, especially with this little shortcut rule I showed you a minute ago, because all of them are just cosine of a linear angle. So we just have to pull out that coefficient as a fraction in front and change our cosines to sines. Now don't forget about that 1/4 in the front. That applies to everything. So the antiderivative for 3 halves is going to be 3 halves x. For my second piece, I've got a 2 coefficient. My cosine changes into sine of the same angle, and I have to bring that 2 out front as a fraction. In my last term, I have a 1/2 coefficient. My cosine turns into sine of the same angle, and I have to bring that derivative out front as a coefficient. And then the last thing I'm going to do, I'm going to clean this up a little bit, combine my coefficients. 1 I'm going to finally end up with 3/8 x plus 2 times a half is just 1, but I still have to distribute the quarter. So here we just have a quarter sine of 2x. Here we get an eighth, but then we're distributing another quarter, so it ends up as 1/32 sine of 4x plus c. So it's possible you'll have to use this power reducing formula several times within one problem, especially if you have an even power that is bigger than 2. We can split it up and replace them individually, but before we can integrate, we've got to FOIL it back out, and that's going to produce another even power. And then we just have to keep doing that until all of those powers are gone, and finally we'll just have these individual little trig functions that possibly have different angles, and those are easy to deal with when we do our antiderivative. In our next video, I'm going to talk about what to do with our other trig functions, tangent, secant, cosecant, and cotangent.